This is a preview, or rather a summary, of the full explanation, but it's possible I will die of old age before uploading the complete video with a full-fledged simulation of the fields around the ring. What I call the Romer-Lewin ring is a deceitfully simple circuit composed by two resistors with different values connected in a ring placed around a region of space where the magnetic field is changing in time. The peculiarity of this circuit is that it shows how, when the electric field is no longer conservative, voltage becomes path-dependent, and it is no longer possible to define a potential function for the total electric field. We can still define a scalar electric potential, but we will see what it means. In particular, when we take 2 points A and B on the circumference, the voltage between A and B along the path going through the small resistor will be different from the voltage between the same 2 points along the path passing through the big resistor. When the source of the changing magnetic field is a long solenoid, ideally an infinitely long one, induced electric field can be determined analytically with little effort. From the experimental point of view, I found it easier to use a toroidal solenoid wrapped around a toroidal magnetic core. This setting doesn't have a simple analytical solution, and the field has a slightly different configuration in space. This means that a different surface charge configuration will have to compensate for the symmetry between field and circuit geometry, but it won't alter the results. As a matter of fact, the experiment with the long solenoid is done, or rather shown, in Purcell's third volume of Berkeley Physics, Electricity and Magnetism, while the experiment with the toroid is done in Hausen-Melcher's Electromagnetic Fields and Energy from the MIT OpenCourseware. The whole book is downloadable for free from the OCW MIT website. And this was just to flex a bit of authority principle. In my case, I used the core of a toroidal transformer whose primary coil is connected to 230 volts 50 Hz mains line. The rate of change of the magnetic flux is low enough that the whole experiment is considered to be in a quasi-static condition, a magneto-quasi-static condition to be precise. Roughly speaking, this means that the change in magnetic field can link an appreciable change in electric field, but that this electric field is neither strong nor fast enough to link an appreciable magnetic field. In this experiment, there is neither radiation nor retardation effects. It is neither an antenna nor a transmission line. And while we can invoke the concept of mutual inductance to explain the current flowing in the ring, or if you will, the voltage when the circuit is open, the self-inductance of the ring itself is so small that at the operating frequency we can completely neglect its effects. As a matter of fact, the current in the ring will be so small that the magnitude of the magnetic field associated with the current will be negligible. It will not alter the field in the core, and we will not have to worry about linking any appreciable flux in the measuring loops. To summarize, with these small change in fields, the only appreciable magnetic field present will be confined inside the core, and the only appreciable field in the space around and inside the ring itself will be the electric field. For completeness, I also have to specify that the ring and the core are both stationary with respect to each other and observer. There are no motional effects involved. Oh, this was just the introduction. So, how is this electric field shaped? We can say for sure that it will be sinusoidally oscillating in time at a frequency of 50 Hz. But in order to know the electric field's spatial configuration in space around the ring, we need either a good amount of math or a numerical simulation, especially when the ring is a three-dimensional object. Things can be simplified a lot if, as a source of the magnetic flux instead of a solenoid wind around the toroidal core, we consider an infinitely long solenoid. The analytical solution for the fields becomes more easily accessible. And even better, if we reduce the problem to two dimensions by considering not only the driving solenoid infinitely long, but also the ring and the resistors that will form a long cylinder wrapped around the solenoid, the solution becomes even simpler. I'm not going to solve it now. This is just a preview. And what I'm going to show you is that the two-dimensional representation of the electric field inside the ring, that is, inside the copper conductor wires and inside the resistors, which we will consider made of uniform isotropic material of constant section. Keep in mind that this is a snapshot at a given instant in time. The actual field varies sinusoidally at 50 Hz. So you have to imagine these arrows to cyclically vary in amplitude from maximum in the clockwise direction to zero, then to maximum in the counterclockwise direction, then back to zero, and so on. All arrows change at the same time, meaning that there is no propagation of the updating of their values. We are considering a quasi-static system where there are no propagation, retardation, or radiation effects. From the values of the electric field, we see that the electric field is very small in the copper, in accordance to Ohm's law in a very good conductor, ideally zero. It is significantly stronger in the smaller resistor and much, much stronger in the bigger resistor. Most importantly, the electric field lines are closed lines. They do not originate from positive charges and end in negative charges, like in the case of the electrostatic field. They go in a circle. They pass, so to speak, through the charges. This is a consequence of the fact that due to the presence of the changing magnetic field, the electric field is no longer conservative. This is the reason why KVL ceases to work in this context. Even without getting into the math, it is instructive to see how the system ends up with a resulting field shaped like that. The total electric field is a superposition of two components, a circulated induced electric field and a Coulombian conservative electric field. The former is the field that is induced by the change in magnetic flux, and that would be present in the space occupied by the ring, even when the ring itself is not there. When the ring, with its two resistors, occupies that space, the induced electric field sets charges into motion, and these charges redispose themselves so quickly that we consider the change instantaneous. They do redispose themselves on the surface of the ring and at the interface between materials of different conductivity. The effect of these surface and interface charge is the creation of the second component of the total electric field, a component that behaves like an electrostatic field. This is the Coulombian component that is generated by positive and negative charges, starts from the positive charges and ends in the negative charges. And this is the component that can be expressed by a scalar potential. In this picture, I show a pictorial representation of the interface charge, and I show the Coulombian electric field line starting from the positive charges and ending in negative charges. The surface charge is not shown for simplicity, but be aware that surface charge on the lateral surface of the conductors and resistors is needed not only to steer the field inside the ring and make it follow the circuit shape, but also to fix its magnitude and make it uniform throughout the transversal section. We are also neglecting the skin effect, of course, because the frequency is considered so low. It might be helpful to notice that a redistribution of charge and the creation of this electric field is analogous to what happens in electrostatics when a conductor is placed in an external electric field. The charge on the surface move and redistribute itself in order to create a field that will make the total field inside the conductor zero. In magneto-quasistatics, the redistribution has the goal of creating a field that will satisfy Ohm's law in its local form inside the conductor and the resistors. When we consider the effects of both fields acting together, their superposition, we will get the configuration of the total electric field as shown in this picture. And it is this field that describes the complete physical system. There is a negligible total electric field inside the copper conductors, compatible with the high conductivity of copper, and ideally zero in a perfect conductor. There is a strong field inside the small homogeneous resistor, and a much stronger field inside the larger homogeneous resistor. Notice that the field changes abruptly at the discontinuities, and that its field lines do not appear to only exit positive charges or only enter negative charge. The total field, in fact, is not conservative, and as such, it does not admit a potential. Mathematically, we need both the scalar electric potential phi that describes the Coulombian component E cool, and the vector magnetic potential A that describes the induced component. This figure summarizes the whole ordeal. Two components of the total electric field superpose to give the actual field, the field that is felt by electrons in the material and in the space around it. The configuration in space will require a little bit more of mathematical wizardry. What is important to notice is that neither the induced nor the Coulombian components tell the whole story. They each tell half of it. This is true for the fields themselves and also for the potentials that are associated with them. That is the magnetic vector potential A and the electric scalar potential phi. Mathematically, we can express the dependence by both potentials in this way, with this formula that showed that the total field is the sum of minus the time derivative of the vector potential plus minus the gradient, that is the special derivative of the electric scalar potential. This relation can be derived from Faraday's law, and what it tells us is that the scalar electric potential phi only carries a part of the information required to completely describe the physical system. Now, this video is already too long, so the part relative to how to compute the voltage in any part of the ring will be put in the following video. I apologize, but synthesis has never been one of my qualities.